Welcome back once again to real-time digital signal processing course. So today we will discuss about IIR filters. So as a recap, in the last two classes we discussed about FIR filters, their linear phase and how we can represent them, how we can design using the window techniques. So today we will see a little bit on recap of FIR filter, that is we said it is a linear phase filter. So the importance of it, as you can see with an example in the speech signal, we use phase differences in arrival to locate the speaker. So in this case it is we may not need the phase part of it if there is any delay in the thing. So you locate them, that is we call it as delta D is equal to C into delta T. So this is how the speaker think, and then our ear automatically adjusts to whatever there is a delay in the phase of it. That is what it is shown here. One speaker is located, ears are relatively insensitive to phase distortion in speech from that speaker. So this is used in speech compression and cell phones. Where linear phase is crucial, we will see in the audio signals, in images and in communication systems. So in these cases we need linear phase response filters, FIR filters, and then a realizable IIR filters cannot achieve this linear phase response over all frequencies. So coming to one more example of where the phase is important, that is vital visual information in phase is shown with the MATLAB original image here. So when you take the FFT of the image and set phase to 0 and take inverse FFT, as you will be seeing, only you will be seeing the blank, that is a black in this case, no picture whatever was in the originally seen. Whereas if you take the FFT of the image and set magnitude to 1, take inverse FFT, keep imaginary part. So this is how the imaginary part looks like when you take the IFFT, and this is with respect to real part if you take IFFT. So combined will give us the original image. So coming to representation of our finite impulse response filters, we know that duration of impulse response h of n is in this case is finite. So this is 0 valued for n outside interval 0 to m minus 1. So we say that y of n is nothing but x of n into convolution with h of n, which is represented in the sigma notation in this way, and then this is minus infinity to infinity. So in our case FIR filter is going to be, because we will be designing order of the filter is m. So the summation will be between 0 to m minus 1. So in this case output depends on current input and previous m minus 1 inputs, and summation to compute our y of k reduces to a vector dot product between n input samples in the vector domain as it is seen here. X of n is represented in vector, and then our impulse response is represented in vector, then it is going to be a vector multiplication, what we will call it. So we know that filters play many roles, we have seen the thing. Just to give one more brief look at the thing is noise removal, signal and noise spectrally separated basically in that case. Example is we can use band pass filtering to suppress out of band noise, and in the case of analysis, synthesis and compression, so for we use a spectral analysis basically to see how much of data what we need it and which are the ones we can do the compression in the frequency domain. Other method is in the spectral shaping. So that is in basically for data conversion we use the filters, and for the channel equalization we know that in communication input channel has to be reconstructed. So we take inverse filter basically there and then do the channel equalization, whatever noise coming out of the channel. And then in the symbol timing recovery also we will be using the filters, and in carrier frequency and phase recovery we need filters. Coming to next is the infinite impulse response IIR filter. So, we see that impulse response of infinite duration, that is what we call it. So, what does that mean, we will be seeing in a while. So, if I give the impulse response h of n is equal to half to the power of n into u of n, that is the step function. So, the same thing in our frequency domain or in the z domain, what we represent is h of z, which is n is equal to 0 to infinity half to the power of n into z minus n. So, which we will be representing it as change it to 0 to infinity. So, expand the summation, which becomes 1 plus half z minus 1 plus etcetera. So, we will be getting 1 by 1 minus half to the z power minus 1. So, how to implement this IR filter by computer, what we will look at it. So, we say let x of k be the output signal and yk the input signal, and then yk be the output signal. Then what happens, their z domain representation is going to be y of z for our output and then x of z. Then the impulse response h of z in the z domain is represented as yz by x of z. So, or if we want y of z, then we know that impulse response into our input h of x of z. Then what we have taken, this is our impulse response, y of z will be becoming 1 by 1 minus half into z minus 1 into x of z. Then if we simplify the thing, it becomes half into z minus 1 into y of z, that is y of z minus half into z minus 1 into y of z, which is equal to x of z. So, what happens to our, when we take the inverse z transform, what happens to our y of n, which is equal to half y of n minus 1, that is a previous sample, which is equal to x of n. So, if we transform this half y of n minus 1 to the other side, we will be seeing that y of n will be equal to half into y of n minus 1 plus x of n. So, x of n is the current sample and y of n is n minus 1 is the previous output sample, which is used for calculating the current output sample. So, what we say is recursively compute output y of n for n greater than or equal to 0, given y of minus 1 and then x of n. So, how we can represent this filter in a different way? So, we will be seeing the difference equation first. So, y of n is given as half into y of n minus 1 plus 1 by 8 into y of n minus 2 plus x of n. So, that is we are going to do the recursive computation needs. What are the input values, what we need is y minus 1 and then y minus 2. For the filter to be linear time invariant, so we assume that y of minus 1 equal to 0 and y of minus 2 equal to 0, and the block diagram to represent this difference equation is shown in this figure. X of n is the input and y of n is the output. So, with the delay we will be generating y of n minus 1, which is going to be multiplied by half, and then other unit delay will give us y of n minus 2. So, which is multiplied by weight vector 1 by 8. So, all the three are getting summed up and then we will be taking y of n as the output. So, the transfer function, what we say is it assumes a linear time invariant system. So, y of z is represented as half into z minus 1 into y of z plus 1 by 2 into z minus 2 into y of z plus x of z, and impulse invariance response of this is given by y of z by x of z, which is nothing but 1 by 1 minus half into z minus 1 minus 1 by 8 into z minus 2. So, we say that poles are at minus 0.183 and plus 0.683. So, how we are going to design this? We say it is designed with respect to biquad 0, Z0 and Z1, and poles will be represented as P0 and P1. So, always we use the biquad section. So, in that case how it is going to represent it, h of z is given by C is the weight factor what we have it, z minus z naught into z minus z1 by z minus p naught into z minus p1. So, how we represent the magnitude response? We will be taking in the frequency domain, we substitute z is equal to e power j omega, then take the magnitude response. So, our z is equal to e power j omega has to be put in here also, and this represents our magnitude response. And then we say that magnitude of A minus B is distance between our complex numbers A and B, and e power j omega minus p naught magnitude is a distance from our point on unit circle e power j omega and pole location at p naught. So, that is how we represent the thing. When poles and zeros are separated in angle and poles near unit circle indicate filters pass bands, and zeros on near unit circle indicate the stop band. So, we can see that how the poles and zeros have to be placed to achieve our pass band response, and then the stop band attenuation how we can arrive at. So, coming to biquad example, continuing with the thing, the transfer function is given by this equation, and when transfer function coefficient are real valued, then poles we say x are conjugate symmetric or real valued, and then zeros we represent it with 0 or conjugate symmetric or real valued. So, filters below have what magnitude response? One has to answer this. So, what you see is these are the two complex conjugate poles here, and corresponding zeros are outside the unit circle. This is our real axis and this is our imaginary axis. So, as we say that zeros are on the unit circle basically, and here you will be seeing that poles and zeros are inside the unit circle, and the other one you will be seeing it poles are inside whereas zeros are outside the unit circle. So, poles have radius r, zeros have radius 1 by r, that is what we represented. So, we have what kind of filters we can design using IIR method or FIR method: low pass filter, high pass, band pass, band stop, or all pass, or even notch filter, what we can design the thing. So, first we will see the direct form IIR realization, how it is going to be represented. So, rational transfer function what we call it. So, our impulse response h of z is given by y of z by x of z. So, we say that b of z represents our zeros and a of z represents our poles. So, which is given by b naught plus b 1 into z minus 1, b n will be z b n into z minus n. So, we have n zeros and we say m poles. So, 1 minus a 1 into z minus 1 plus etcetera or minus etcetera a m into z minus m. So, which implies that my y of z is represented as 1 minus sigma small m is equal to 1 to m a m into z minus 1. So, this is my represents my poles basically, which is equal to x of z into this will be varying k is equal to 0 to n, b k are the zeros into z minus k. We say direct form realization, that is dot product of vector of n plus 1 what we are assuming it, coefficients and vector of current input and previous inputs what we call it as FIR section for our zeros, and dot product of vector of m coefficients and vector of previous m outputs. So, that is FIR filtering of previous output values, what we will be taking it here as it is represented, and then computation of m plus n plus 1 multiply accumulate what we need it as we can see the thing, and memory is also going to be m plus n words for previous inputs and outputs, and then m plus n plus 1 words for the coefficients as it is represented here. This is our previous output, and this is our input represented with the coefficients bk. So, when we represent this equation in this form, what happens to our structure? We will see x of n is the input, and we see that b naught, b1, b n coefficients are in the feed forward. So, we have the unit delay, and this is x of n minus 1 to x of n minus n, which are going to be summed up in this unit, and then output is going to be r y of n. So, what is the feedback here? So, we will be delaying with 1 unit delay, and coefficient is going to be multiplied with a1. So, we will be a1 into y of n minus 1. So, which goes up to y of n minus m into am. So, all this is the, we call it as the feed forward path, and this is the feed backward path. So, completely added here, if there is, as we have seen in the earlier case, it is minus a1 into r y of n minus 1. So, some of the coefficients, as we will see, they may add and then get subtracted, and then they may nullify, and we may not have the overflow, may or may not, we can tell that y of n may be overflowing or not overflowing in these cases, depends on the coefficients what we are using it. See, we call it as when we want the full precision. So, what we need is word length of y of 0 is going to be 2 words. So, as we have seen the thing, multiplication and then addition. So, it will be going up to 2 words. So, what happens to word length of yn if we start putting y of with 2 words, we will be seeing the output next time is going to be 4 words, or it goes on increasing. To avoid this, what we have to do is we have to come back our yn representation with whatever n bit representation, so that we are not going to have overflow in our representation of y of n. So, and then m and n may be different, we do not know what kind of order of the filter we are going to design. So, they may be same, or they can have different values for them. Then how we are going to represent again the direct form of IIR filter as it is shown here. So, we will be rearrange transfer function to be cascade of an all pole IIR filter followed by an FIR filter. So, that is y of z into x of z into b z divided by a of z. So, we represent this as a v of z, x of z by a of z as v of z into b of z, where that is what v of z is given by this equation. And then we say here v of n is the output of an all pole filter applied to x of n. That is what we call it. So, v of n will be x of n plus all the poles m into v of n minus m, basically m will be varying 1 to m, and y of n you will be seeing that it is represented with our zeros multiplied by v of n minus k. So, the implementation complexity, we can assume m can be greater than or equal to n. Then number of computation what we need is m plus n plus 1 max in this case, and memory is going to be m double words for past values of En and m plus n plus 1 words for the coefficients. How this is going to represented, as you can see here, this is our v of n point, and we have summation here and summation here. So, x of n is going to be multiplied with all IIR filter feedback basically, that is this is the feedback structure. So, V of n minus 1, V of n minus m, which is going to be summed up. So, which is going to be given as you will be seeing that is our V of n, which is getting multiplied, we will be seeing that Bk into V of n minus k with that, and then summed up here with all feed forward are zeros and y of n will be output. So, as you notice from single summation what we have come down to double summation. So, the critical path what we call it is or overflow or underflow, because here all of them are negative, we may underflow in this case, and all of them are positive, we may overflow also. So, these are the two critical nodes what we call it. One has to take care that summation is not going to overflow or underflow in these 2 points. From one single critical node we have bifurcated into 2 critical nodes, but as you can see that the delay units have come down by 2 compared to the previous direct form structure representation. So, that is what the advantage. Now comes with the stability, because we are more worried with respect to stability. So, we will be seeing that our linear time invariant system is what we say is bounded input, bounded output, Bibo stable what we call it. So, if for any bounded input x of n such that x of n is within this bounds what we call it between x of n is less than or equal to or some bound value which is less than infinity, then the filter response y of n is also bounded what we claim it, that is whatever B2 it should be less than infinity. So, coming with the FIR filter, that is h of n what we have it. So, we said x of n is bounded already, then when the FIR filter is going to be stable, that is Bibo's stable, if and only if what we claim is magnitude of our impulse response h of n is less than infinity for n is varying from minus infinity to infinity. So, we say every finite impulse response of LTI system even after implementation is going to be bounded input, bounded output stable. So, we say causal infinite impulse response LTI system is Bibo stable if and only if its poles lie inside the unit circle, that is what the meaning of it. So, continuing with the thing. So, what we says is rule 1 is for a causal sequence poles are inside the unit circle, applies to Z transform functions that are ratios of 2 polynomials, or the rule 2 is unit circle is in the region of convergence. In continuous time imaginary axis would be in region of convergence of Laplace transform what we claim. As an example, a to the power of n into unit step function, when we take the Z transform of it, which is nothing but 1 by 1 minus a z minus 1 for all magnitude of z greater than magnitude of a. So, stable if magnitude of a is less than 1 by rule 1 applying it, or equivalently stable if magnitude of a is less than by 1 by rule 2 also, because magnitude of z is greater than magnitude of a and magnitude of a is less than 1. So, that way we will be achieving the stability. So, we will see how we can represent z and then Laplace transform what is the relationship. So, that is transform differential equations into algebraic equations that are easier to solve. So, our complex valued functions of a complex frequency variable, what we call it as Laplace in transform, what we represent S is equal to sigma plus j 2 pi f, whereas in the Z transform we will have Z is equal to R into e power j omega. So, the transform kernels are complex exponentials, eigenfunctions of linear time invariant systems, what we call it. So, we have Laplace is equal to e power minus st is equal to e power minus a small sigma t minus j 2 pi f t. So, which is nothing but e power minus sigma t, and then these are the exponential function, two exponential function what we are representing. So, in the z domain what we have z minus n is equal to r into e power j omega to the power of minus n, that is z we are replacing with r into e power j omega. So, which is nothing but r power minus n and then e power minus j omega. So, we constitute that e power minus sigma t and then r minus n as dampening factor, whereas the other exponential factors e power minus j 2 pi f t and e power minus j omega n are the oscillation term in our representation. So, no unique mapping from Z to Laplace domain or from Laplace to Z domain. So, we can have mapping one complex domain to another is not going to be unique, and one possible mapping is impulse invariance. So, make impulse response of a discrete time linear time invariant system be a sample version of the impulse response of the continuous time LTI system. So, what is that? I have a function f of n. So, in the z domain I represent pass it through with h of z, that is my impulse response, and what I will get output is y of n. Whereas, in the case of Laplace transform, so we will be continuous time signal is represented with f tilde t, which is transformed using h of s. So, I will be getting the y of t. So, how do we represent in that case? H of s is given as h of z at z is equal to e power s t, that is we call it as impulse invariance mapping. So, coming to the mapping, how it is going to happen in the impulse invariance, what it is shown here. Mapping is z is equal to e power s t, where t sampling time what we call it as T s basically. So, we will be seeing the axis, our real axis and then imaginary axis. The poles on the left hand side of our what we call it as Laplace transform, which is going to be mapped inside the unit circle, and our imaginary axis, which is shown in blue actually, s is equal to j 2 pi f t, gets mapped on the unit circle, which becomes 1. And then the zeros on the right hand side of it can be mapped to outside our unit circle. So, this is how from Laplace transform to Z transform the transformation is going to happen. So, what we have is omega max is nothing but 1 in this case, which is f max, which is given by 1 by 2 pi f, which is implied that f s should be greater than 1 by pi. So, we assume let f s is equal to 1 hertz, what we are assuming it. Then what happens are poles s minus 1 plus or minus 1 j in the is getting mapped in the z domain as 0.198 plus or minus j 0.31 into t minus 1 second. So, zeros will be getting mapped as s minus 1 plus or minus j is getting mapped as in the z domain 1.469 plus or minus j 2.287 into t minus 1 second. So, you will be seeing the Laplace domain left hand plane inside the unit circle, which we discussed, and imaginary axis is the unit circle, and right hand plane is going to be our outside unit circle. So, what we say is with this we will be having low pass, high pass, band stop, all pass or notch filter, what it is going to be designed. So, how we are going to represent our continuous time IIR Biquad section. So, second order filter section with 2 poles and 0 to 2 poles, what we can have 0 to 2 zeros. That means to say I need not have to have any zeros in our second order filter if m and n are different. If they are equal, then we will be having 2 poles and then 2 zeros, and that is what we will be representing. And in the transfer function is a ratio of 2 real valued polynomials what we consider, and then poles and zeros occur in conjugate symmetric pairs. And what we define the quality factor, it is a technology independent measure of sensitivity of our pole locations to perturbations. For an analog biquad with poles at A plus or minus JB, where A is less than 0, then the quality factor what Q is given by root of A square plus B square divided minus 2A, where it is going to be half less than or equal to Q, which is less than or equal to infinity. So, if we have the real poles, then B will be 0. So, the quality factor will be half, that is we call it as exponential decay response. And if we have imaginary poles, A will be 0. So, Q becomes infinity. So, we say we are going to have the oscillatory response. Thank you.